So, by the way, this slide is already available from my homepage. I hope just by Googling my name, I think that's really, anyone can get it. And I think I will send this to maybe Dave later on and make it available also from the homepage. Okay, then let me, first, I'd like to thank organizers for giving me a chance to talk here. I'm very happy to have this chance because of the time difference, I usually cannot attend the seminar series, but of course, I sometimes watch the video uploaded on the seminar webpage, so very happy to talk here. So today's talk is a kind of survey talk. I'm going to try to survey recent development of cyber-weakness theory for armies of smooth form manifolds. And in the next talk, I will focus on more specific research with Masaki. But today I will try to survey some kind of comprehensive talk. Okay, so this is contents. So first I will give a quick introduction, and later on, thank you. Yeah, and so later on, I will explain some two big methods, giving some constraints on smooth families for manifolds and considering invariants, detecting some exotic type phenomena. So these two methods are already, of course, used for single form manifold in unparameterized normal gauge theory. But some similar kind of thinking holds also for families. So I will explain that kind of thinking. And as the last part, I will focus on this first half, the constraint. So constraint, giving constraints on smooth families for manifolds and extracting some information about the difference, some sort of difference between the diffeomorphism group and the homeomorphism group. Okay, so then let me first start with the introduction. So here's a motivating fact. So the comparison between the diffeomorphism group and the homeomorphism group in dimension are less than or equal to 3. So first, so here is a well-known slogan for most topologists, I think. So probably most of you have heard of the slogan that there's no essential difference between C0 category and the C-infinity category in dimension less than or equal to 3. For example, the typical fact representing this slogan is probably that if you have a topological manifold of dimension less than or equal to 3, then your topological manifold admits a smooth structure essentially uniquely, just up to isomorphism. So in such a sense, people believe that there's no essential difference between these two categories in such a lower dimension. And so here I want to say, so this is true also for automorphism groups in the following sense. So as a notation, for a smooth manifold M, let me denote by diff M, the group of diffeomorphisms. Precisely this guy is equipped with C-infinity topology. And if I denote by homeo M, that means the group of homeomorphism with C0 topology. And here's a fact, big fact. This is a collection of a bunch of theorems by various authors. Let M be a closed, smooth, orientable manifold with dimension less than or equal to 3. Then here's a natural map from diff to homeo. So precisely this inclusion notation could be a little confusing because this group diff M is equipped with C-infinity topology, as I said, and homeo M has C0 topology. So this inclusion is just an inclusion as a set, but at least this is a continuous map, of course. So you may ask if this map is like weak homotopy equivalence or homotopy equivalence or not. And as a fact, in such a lower dimension, this natural map is actually a weak homotopy equivalence. So it means that in such a lower dimension, in some sense, there is no homotopical difference between these two huge groups via this natural map. So it's very natural to ask what about dimension greater than or equal to 4. Okay. So let me first little mention higher dimension. So higher dimension occurs in dimension greater than 4. There are many examples of where this map is not a weak homotopy equivalence. Okay, so contrary to this, it's the situation become quite different. For example, once you have an exotic sphere of high dimension, then as a corollary of H-coordination theorem, your exotic sphere can be obtained just by gluing two disks using a diffeomorphism on the boundary sphere in minus one dimensional sphere. And if your sphere is exotic one, then it means that the diffeomorphism which was used to glue these two disks is kind of exotic stuff. So exotic here means it extracts some difference between diff and homeo. So once you have a higher dimensional exotic sphere, you may detect some difference between diff and homeo. And but basically, in this talk, I want to focus on dimension 4, the lowest dimension where such phenomena happens. In dimension 4, as far as I know, probably the Casey surface is the first is such example, and this was proven by Donaldson. So I will explain this result later more precisely. And actually, nowadays there are so many such examples. So that's what I want to talk. And so I think even there's no counterexample to the following. This might be too optimistic conjecture is known. So the conjecture says that the for arbitrary m smooth manifold dimension greater than or equal to 4, this map is not a weak homotopy equivalence. So comparing the above factor in lower dimensional case, dimension less than or equal to 3. So this can be a little bit too optimistic, but just I don't know any counterexample for this. And the main topic of this talk is recently in dimension 4, the lowest dimension in this conjecture, many results to support this conjecture were obtained by cyber-Witten theory for families. So mainly today, maybe I will just list up many results and maybe no time to explain like precise proof, but in the next talk, I will try to describe relatively precise proof for one of those results. That's the work with Masaki. Okay, so this is the end of this short introduction. So no questions so far. Okay. All right. So then let me go to the next topic. So these two, just comparison between these two methods, giving constraint on some structure and giving invariant, which is sensitive about some structure. Okay, so to explain these two methods, comparison between these two methods, I wanna first describe Ari's result about comparison between diffeomorphism group and the homeomorphism groups in dimension 4. Okay, so here's a theorem. This was proved by Donaldson in his paper where he introduced Donaldson's polynomial invariant, 1990. The natural map. So this map between pi 0 is the natural map induced from the inclusion from diff to homeo. And this natural map is not a solution. So this is a result of Donaldson. And this was proved by looking at the action of diffeomorphisms on the Donaldson invariant. And so nowadays, it can be also shown also by cyber-Witten invariant as well. And actually, the cyber-Witten proof is more easier, but yeah, as you can see, this was proved before cyber-Witten came. Okay, but basically, this theorem's proof, original proof, was just inside the standard gauge theoretic framework. But here is some fascinating idea, that is to develop gauge theory to families of four manifolds. So by the word family, so just I mean fiber bundle in this talk, just fiber bundle. So fiber bundle with 4-manifold fiber. Okay, so usually, of course, as you know, the gauge theory was developed for one single manifold, but just consider a parameterized version, parameterized situation. Then on each fiber, at least as far as, for example, as far as you have fiber-wise species structure on the fiber bundle, then you can consider cyber-within equation, or if you have fiber-wise SU2 bundle or SO3 bundle, you can consider fiber-wise ASD equation. And using those equations, extract some information about that comparison between diff and homeo in dimension. So this should be good idea. And the first striking result in this direction was given by Danny Luberman in 1998. So let me set the X to be the connected sum of several copies of CP2 and oppository oriented CP2 for some N and N. So in Danny's result, actually, these M and N can be seen more explicitly. But just let me simply just like let me write in this way. So for such connected sum, you can show that the natural map between pi 0 diff to pi homeo. This is not an injection. Okay, this is it's interesting to compare this result with our result by Donaldson. Maybe it could be helpful to rephrase just as follows. So this Donaldson result says that you can find interesting homeomorphism of a Casey surface. So interesting here means you can find a homeomorphism which cannot be put into diffeomorphism group by moving topological isotopy as much as you can. Okay, so that's the meaning of this Donaldson result. But on the other hand, this Danny's result means that you can find an interesting diffeomorphism of X, of such X, in the sense that that diffeomorphism is topologically isotopic to the identity map, but smoothly cannot be connected to the identity map. So that's the meaning of this result. Okay. And
Kono, is it true for every M and N, or I'm a little confused about the statement.
Sorry.
So is it true for every M and N, or the choice M and N?
So if I remember correctly, this M should be at least even number. Yeah, at least even, maybe greater than 4. Yeah, greater than 4, even number which is greater than or equal to 4, if I remember correctly. And N should be just sufficiently large. This is kind of, as you know, so this is used for some kind of blowing up step. So N should be greater than maybe around 16 or 20, so some big number.
I see.
So this can be arbitrary big number, but M should be at least even. So because in Danny's construction, this manifold appears as the dissolved form of like the connected sum of some like elliptic subset E of 2n and CP2 2-point blow up CP2, and the dissolving you obtain this form of manifold, but M, there's a constraint on this M. M should be even number, I see. Thank you. Okay, so, and this Danny's result was based on this idea. So the proof of his result is based on the ASD equations parameterized by a one-dimensional space. So essentially, one can regard this parameter space is a circle in this case. Dave wrote a correct number. Thank you. Even and great. Oh, thank you so much. Yeah. Okay. So this is the first striking result of this direction, I think. And so for here, I want to explain these two comparisons. So as I said, the constant and invariant. So these two results by Donaldson and Danny is a typical example to explain this. So first, let me note that actually one can give an alternative proof of Donaldson result. The result saying that this map is not surjection, not a surjection, using Fermi's cyber-within theory. So this was done by Tsuyoshi Kato and Nobuhiro Nakamura and myself and David Baragrier, not last year, 2019. So this alternative proof uses some constraint on smooth families of four manifolds and detects a non-smoothable family, so which I will explain more precisely later on, of K3 family, non-smoothable family of K3 over the circle. So the family version, so in the work with Kato and Nakamura, to detect this non-smoothable family, we used a kind of family version of the 10/8 inequality. And in David Bagrier's proof uses a family version of Theorem BC. So these two things, like 10/8 and Theorem BC, are typical constraint on smooth form manifold. And so one can consider also a family version of that. And using those constraints, one can reprove this Donaldson result. So here's some table to explain this more a little more precisely. So once you have just a single manifold means just not family, just a manifold, then you have a notion of non-smoothable manifolds. As you know, so like the typical example is like E8, any number of connected sum of E8, and so similarly, in the world of families, one can consider notion of non-smoothable families. So I will explain the definition later, soon later, maybe next slide, but just here, let me say it a bit more intuitively. So just like I'm sorry, like non-smoothable manifolds, one can consider non-smoothable families. And very roughly speaking, this correspondence is not rigorous at all in general, but the feeling is that the non-smoothable family roughly corresponds to thinking that the non-surjectivity of this natural map from pi something diff to pi something homonym. And Donaldson's result on K3 is a typical example of this. His result here says that this map is not a surjection. And this can be detected by considering non-smoothable family over circle. So at least this rough correspondence is actually true when you consider family over sphere of some dimension, at least. But in general, this is not true. But the feeling is something like that. And if you consider exotic manifolds, of course, you have a notion of exotic manifolds, so single manifold. And similarly, one can consider exotic families as well. And in the same of rough correspondence, very roughly, some feeling is that this is very closely related to this map is not injective, like pi star, pi something diff to pi something common. So Danny's result is an untypical example. As I said, Danny's result is saying that this map is not injection for this star is equals to 0. And this was done by like considering invariant, or maybe here I'll explain. So this upper row should be detected by considering some constraints, some sort of constraints, such as like Donaldson's diagonalization or Theorem BC or Fruita's 10/8 equality and their family versions. Okay, so for example, when you want to show that this NE8 is not non-smoothable manifold. So here, non-smoothable manifold means just a topological manifold which doesn't admit a smooth structure. So, so if n is odd, then you can use Rohon's theorem. But if you try to show that for all n, then you can use Donaldson's theorem. And anyway, so Rohon's theorem and Donaldson's theorem are both a constraint on smooth structure. And this family story is also something similar, giving some constraint on smooth families of form manifolds. Then you can detect some non-smoothability. And this lower row, this exotic stuff, exotic manifolds or exotic families, this should be detected by some invariance of smooth structure or smooth families, like the Donaldson invariance, about the invariant, or out the invariant, or their family versions. Okay, so of course, to detect the exotic manifold, you have to use some invariant, and similarly, to detect exotic families, in principle, you have to use some invariant. And Danny's result made use of one parameter invariant, one parameter Donaldson invariant. So, so until here, I didn't explain the precise definition of these notions that notion of non-smoothable families and exotic families. So just let me describe those definitions more rigorously. So here's a definition of non-smoothable family. So let X be a smooth manifold, and let B be a topological space. So in practice, in most cases, the base space B appears as a manifold, but in definition, B is not necessarily be a smooth manifold. And but of course, since we are considering a fiber bundle, so maybe it's reasonable to assume that B is like relatively good space, like Hausdorff paracompact or something. But at least not necessarily be a manifold. So let me consider a fiber bundle. So my notation is that is like this, like to describe fiber bundle, like X. If we are like this means X is a fiber and E is a total space, and B is a base space. So this, let me consider topological fiber bundle here. So topological here means the bundle with the structure group, the homeomorphism, reduced to homeomorphism group. And I say that E is a non-smoothable family if E doesn't admit a reduction of structure to the diffeomorphism group. I think this can be a natural definition, I think. And similarly, here's the definition of exotic families. Again, let X be a smooth manifold and let B be a topological space. But here, let me consider two smooth fiber bundles. So here, E1 and E2 be smooth fiber bundles with common fiber and common base. Okay. And I say that these guys are exotic families, exotic with each other if these guys are isomorphic as a homeo bundle, continuous bundle, but they are not isomorphic each other as diffeomorphic bundle, smooth bundle. Okay. It's not so difficult to spell out these definitions, but maybe it's more maybe could it be helpful just showing you these diagrams maybe. So the definition of non-smoothable family just simply means this diagram, right? So now you have a base space B, and once you have a topological bundle, so it means just there's a map from B to B homeo, continuous map here, and here's a natural map induced from the inclusion from diff to homeo, and the definition of let's see. So definition of this non-smoothable family just simply means that there is no lift of this Crash-Wang map of E. Okay. And similarly, exotic families definition is also can be right quickly. Like so now I'm assuming that E1 and E2 are isomorphic as a homeo X bundle. So just let me identify these two as a homeo bundle. Then you have a common underlying bundle here. And this says that these lift E1 and E2 are not homotopic as lift. So this is the definition of these exotic families. And in both situations, these diagrams imply that the natural map from diff to homeo is not a weak homotopy equivalence, of course. So if diff and homeo is a weak homotopy equivalence via this inclusion map, then of course there's no homotopical difference between these two. So of course, such non-existence of lift can't happen, and also this non-homotopic result also can't happen. But so in both cases, you can say that this map, natural map, is not a weak homotopy equivalence, but the way to say that is very different each other, as you see. Okay. So as I mentioned, so easiest example is the case that the base space is circle, just circle. Then some existence of a non-smoothable family, existence of some bundle E, which doesn't admit to this lift, corresponds to that this natural map, Pi0 diff to Pi0 homeo, is not surjection. And similarly, if you consider exotic families E1, E2 over circle, then the existence of such exotic families is equivalent to that this natural map is not injection. Okay. So until here, just I focus on the story about pi0, but of course you may ask, what about example of about more higher dimensional homotopy groups? And so here's one theorem. So the Donaldson one, and here's Daniel's theorem. So as I explained, so these two results are about pi0 between the map from diff to homeo. And this is a non-surjectivity result on pi0, and here's non-injectivity result on pi0. So it's natural to ask, what about n greater than or equal to 1? So as far as I can recognize in public press, like this Watanabe's result seems the first example of this direction. So maybe many of you know that Watanabe gave a disproof of four-dimensional Smale conjecture. And in that paper, he also showed that this natural map from pi1 diff S4 to pi1 homeo S4 is not an injection. And so it's very natural to ask next, what about non-surjectivity result? Here's one example of that direction. So this is a joint work with David Bargrier, 2019. So the natural map from diff of K3 to, pi1 diff of K3 to pi1 homeo K3. So we can show that this is not a surjection. This is not a surjection. So as far as we know, this should be the first example for Michael's X where this natural map between pi n can be shown to be not surjective for positive n. And this was proved using a constraint on smooth families of K3 surfaces. Okay. And yeah, actually around here, there are so many unsolved problems. For example, we don't know that if this map is injection or not. And also similarly, we also don't know that if this map is injection or not. We don't know about that. It should be fascinating, but currently, at least I have no idea how to solve that. Okay. So as I said, this was proved by considering some constraint on smooth families of K3 surfaces. And in the latter half of my talk, I will talk about some results based on such constraints. But before proceeding to that direction, maybe I should at least list up the work obtained by considering invariance, invariance for families. So here's a list. So I might drop some, but at least these are some important and interesting results, I think. First, let me mention that Dani's Ruberman's result. This is kind of lower bound on the four-dimensional Torre groups using one-parameterized equation, polynomial, one-parameter polynomial invariance. So Torre group is usually considered in two-dimensional topology, as you know, like it's a subgroup of mapping class group acting on homology trivially. And you can as well consider a four-dimensional version, just like subgroup of mapping class group acting on the intersection form trivially. And in general, it's quite difficult to detect some non-trivial elements of such group, even in two dimensions. But this Dani's result reveals that actually you can say something about the four-dimensional Torre group. And in his proof, he used one-parameter polynomial, Donaldson polynomial invariant. And after that, Dani gave also a result about a positive scalar curvature metric. Here, as notation, let me denote by the PSCX, the space of positive scalar curvature metrics, space of positive scalar curvature metrics. And Dani shows that in dimension 4, so in this case, this X should be again the connected sum of several copies of CP2 and minus CP2s. And for such a manifold, of course, such a manifold connected sum of several CP2s and minus CP2s admit a positive scalar curvature metric. And that manifold actually, again, maybe there should be some restriction on the number of CP2 and minus CP2. But anyway, Dani shows that the space of positive scalar curvature metrics of such manifold is disconnected in general. So in this proof, he used one-parameter Savaguti equations. And I tried to generalize this result a little bit. So the statement turns like this. In Dani's argument, he used one-parameter Savaguti equation. So instead, one can consider also n-parameter family parameterized by torus, n-dimension torus. And once you consider family Savaguti equation over torus, then the conclusion becomes a little weaker than this one. So this is like non-connectivity, but if you consider n-parameter family, you finally get that non-n-1 connectivity. So of course, the result part become weaker, but by considering the n-dimension family, you can say something another x from Dani's one. So this another means just the different number of CP2 and minus CP2. So yeah, as for asked, so the number of CP2 is get some restriction, but considering some parameter family, you may change it with a number of CP2. So you can say something about another for manifold and yeah, positive scalar parametric space. And after that, David and myself considered some like Savaguti version of Dani's first result. So we can also show that the natural map from pi0 diff to pi0 homo is not injection for some spin for manifold using one-parameter Savaguti equations. So in Dani's original argument, he used the ASD equation, but of course one can also consider Savaguti versions of that. And in the same paper with David, we showed something another thing argued over RPN, real projective space. So let me explain the problem. So we considered again the for manifold of the form of connected sum of CP2 and minus CP2s. And this guy, of course, admits a positive scalar curvature metric. And once you have an involution on this manifold, you may ask if you can find whether you can find this involution invariant positive scalar curvature metric. And obstructing such group action invariant positive scalar curvature metric is a typical application of equivariant index theory. But here we consider the kind of like non-linear version of such an argument. So one can obstruct such like in this case we consider involution, just involution invariant positive scalar curvature metric using family Savaguti equations over RPN. So the source of RPN is very simple. Just this is the final dimensional approximation of the classifying space of 0/2. So if you have an involution on a manifold, you can obtain a family of arbitrary dimensional RPN. Just because simply considering the Borel construction, you can obtain a family over classifying space, and just as a sub of that, you can obtain a family over RPN. And considering Savaguti equations over parameterized by RPN, one can get such a result. Okay. And after this, I think these two results by Kronheim and Murowka and Jianfeng Lin were already given in this seminar series, explained in this seminar series, I think. So Kronheim and Murowka's result says that the dent width of connected sum of two copies of the Kesey surface along this neck is non-trivial in the kernel of this natural map. So again, one can get some example of interesting diffeomorphism, which is topologically isotropic to identity, but smoothly not. But this is very kind of natural example, and yeah, I was actually very surprised when I looked at this paper. Like, quite natural diffeomorphism actually turns out to be non-trivial in this kernel, so it's very surprising. And they used so Bauer-Hutter invariant to detect this one, family Bauer-Hutter invariant. And just after that, Jianfeng revealed that actually this diffeomorphism, this then twist, survives after single stabilization by this connected sum of S2 times S2 in the similar kernel again. So this is also very surprising. So this kind of exotic stuff. As I said, this type of phenomena is like exotic stuff, right? So in this table, it belongs to this lower law, so exotic stories. But Jianfeng shows that actually this exotic phenomena survives after single stabilization. So this is somewhat new. Okay. So here's a list of some work of relating to families invariants. Okay, so I'm going to talk about the constraint next. So is there some questions until here?
So you have a result about that space of metrics on X4 is not n-1 connected for some X4, right? So it's you can, what why are you using families over torus TM?
Oh yeah, so of course if we can calculate an invariant over sphere, it's much better, definitely. Yeah, of course, Tn is actually kind of most kind of bad option to show this kind of result so intuitively. But just the reason why I use the Tn is just in practice, I could calculate the invariant over this manifold. I couldn't find out good example parameterized over sphere or at least more or less connected space over which I can calculate families invariant. Just such practical reason. Yeah, of course. Yeah, theoretically, it's much better if you can calculate families invariant over such as like sphere. Yeah, yeah.
Okay, thank you.
Yeah, thank you. Okay, so any other question here? All right, then let me go on. So next, I'm gonna focus on some constraints on smooth families of four manifolds. Sorry. All right, so here are a list of some recent results about constraints on smooth families of four manifolds. The first one was done with Tsuyoshi Kato and Nobuhiro Nakamura. So this work gives you a first example of non-smoothable families detected by gauge theories for families. So as I mentioned, we use a kind of family version of 10-byte inequality, but I have some hesitation to say this because it's applicable to only very limited situations only. And just soon after this, maybe just 1 month later or something, so David extensively extended the result above by considering family versions of Donaldson's diagonalization. And as a result, as a consequence, it says that this map from diff to homeo is not a weak homotopy equivalence for most of the, so most of it can be a little misleading, but yeah, intuitively, most of the simply connected closed form manifold is very big result, I feel. Yeah, I will explain that.
You will explain that?
So, sorry?
Will you explain that, what most means here?
Yeah, I will explain. Yeah, actually,
okay.
It's okay to show now. Very easy to show, like this one. So this is a precise statement, like yeah, oriented cross simply connected is assumed, and we have to also assume indefinite, and also we have to assume that the absolute value of the signature is greater than 8. But then you can conclude very large class, of course. So currently, as far as I know, there's no way to attack like definite for manifold, and also this signature condition seems not so easy to be removed. But anyway, assuming the two conditions you can conclude.
And do you work also with these elliptic fibrations for that theorem? Is that
Elliptic fibration? Yes.
Is that how you do it?
Sorry, I may.
Do you use elliptic fibration and compare them to connected sums of CP2s and CP2 bars?
So this case is not like this. So sorry, are you asking this Dave Barrier result or another thing? Sorry, are you asking this result or another? Sorry.
In a sense, I'm asking, what classical. I don't know. I'm just wondering whether that corresponds to one of these classical families that are known of homeomorphic but not diffeomorphic four manifolds.
This is not like this because so yeah, here I can use this table maybe. So this Bargurius result is in here. It's some detected by non-smoothable families. But like elliptic fibrations or something like should be around here, exotic stuff. Like for example, the Daniel Luberman's result is belonging to here. Like elliptic fibration with some dissolved stuff. So this is a story relating to invariant. But the David result is belonging to here.
Okay. Thank you.
Yeah, thank you. Okay. Yeah, so then let me explain. So yeah, I will, as I show you, I will explain this David's result later on more precisely because that is necessary also to explain result with Masaki, which will be the main topic in the next talk. So I'm going to explain David's result more very precisely. And after this David's result appear, I worked with Nobuhiro Nakamura to extend David's results to some class of non-simply connected for manifold using pin minus the monopole. This is a kind of variant of Sagawiti monopole equation introduced and studied by Nakamura. And a feature of this variant of monopole equations is this guy can capture some kind of like stabilization by non-simply connected manifold, such as like surface times surface cross surface, or like S1 times three-dimensional manifold. So we tried to extend David's argument to Nakamura's pin-to monopole equations. And after that, I worked with Masaki to extend Bargurius result to four manifold with boundary. So this is the next topic, the topic in the next talk. Okay. Okay, so let me first start with this one, the work with Kato and Nakamura. So here is an explicit example of non-smoothable families. So let me set the XB topological manifold given by this. The connected sum of here minus E8 denotes just the negative definite E8 manifold, 2 copies of minus E8, and M copies of S2 times S2. And here, let me suppose M is greater than or equal to 3. So this lower bound is very easy to explain because so I want to consider the situation that X is smoothable as a manifold. So if you suppose M is greater than or equal to 3, of course this X is homeomorphic to K3 connects sum M minus 3 S2 times S2. But this upper bound less than or equal to 6 is quite technical, so I'm not going to explain. This is necessary, but very just by technical reason. And the theorem here says that you can find non-smoothable families over torus of dimension m minus 2. So more precisely, you can find a continuous bundle which is non-smoothable with respect to any smooth structure, any smooth structure. Of course, as you know, K3 admits exotic structure a lot, and And if I remember correctly, if n m is 5, so if n m equals to 5, you can also find the exotic structure on this manifold. But this theorem says that including for such exotic some structure, this boundary is non-smoothable. And other immediate corollary from this theorem is that for any smooth structure on this X, this natural map is not an isomorphism for some n from 0 to n minus 3. So the proof of this corollary from this theorem is very easy, just by looking at this diagram. So since now we have sorry about this small character. So this currently the base space is m minus 2 dimensional torus. And we have this diagram. So we have crash-finding map into the B Homeo, and we can say that this doesn't lift up to be diff. And just by considering standard obstruction theory to this, then you can conclude that between B diff and B Homeo, we have some homotopical difference up to until m minus 2, just dimension of this torus. But since now I'm taking B, so taking who B, one shift happens, and you can say that between diff and Homeo, there's some homotopical differences from between 0 and n minus 3. But in general, there is no good way to detect in which n specifically this difference happens. Okay. And here's a remark. So the case that m equals 3 recovers Donaldson result, which I explained. So also this could be a little bit overkilling, but anyway, it's also an alternative proof. And as I said, in Donaldson's original argument, his argument, if I remember correctly, that argument cannot be applied to exotic K3 surface, but our argument also covers also exotic K3 surface. So of course I should explain how to construct such.
May I just comment? I would think that I mean Donaldson's argument about K3 is just using the non-triviality of a certain. Well, he says Donaldson invariant. Probably the same argument would work with some K3 invariant. Sorry, some Seiberg-Witten invariant. And since you know for at least for the case there's the result of I guess Morgan and Szabo that says that it's always going to be non-zero. So I would have thought that that would work. That Donaldson's result would work for arbitrary K3 surface. You know, arbitrary homotopic K3 surface.
Right. Sounds good. Yeah.
Because it's really all about the orientation of the moduli space. That.
Wait a second. Yeah. At least Donaldson's. Oh yeah. Wait a moment. So just a flipping orientation. So yeah, Wong and Szabo's theorem says that this even after taking model 2, the invariant doesn't vanish for arbitrary homotopy K3. So flipping orientation. Oh yeah, that should be. Thank you. Yeah, thanks, Danny.
Yeah.
So that Seiberg-Witten proof is very simple. It's also applied to arbitrary homotopy K3. Yes, thank you about that. Okay. So, and as I explained, yeah, actually this result finally will be also covered by the forthcoming Davis result anyway. So yeah, as these comparison result, it will be covered just by Davis result. But anyway, let me explain as a first example of this kind. Yeah, maybe construction can be important for this kind of thing, but yeah, actually it's very simple how to construct. And the idea of the construction goes back to Nakamura's study on non-smoothable group actions around 10 years ago. And it's very simple to explain. For simplicity, let me consider the case that the number of S2 times S2 is 4, just 4. This is not an essential section, just for simplicity. And it's easy to find diffeomorphism, orientation preserving diffeomorphism F of S2 times S2 such that F has a fixed disk, and F reverses homology orientation. So it's really easy, and probably there are so many ways to construct such F. But so one explicit construction of F satisfying these two properties is as follows. Let me start with complex conjugation on CP1 and regard S2 times S2 as CP1 times CP1, and take complex conjugation on both factor. Then it reverses homology orientation. And this complex conjugations have non-empty fixed point set RP1 times RP1, and take one point in RP1 times RP1 and deform it by isotopy a little bit. Then you can get a fixed disk, and of course it preserves these conditions of F reverses homology orientation. So this is one explicit construction, and define two homeomorphisms F1 and F2 by the following picture. So now I assume that this F has a fixed disk, and let me put a fixed disk around here to take connected sum, and then take a copy of F over here, and extend F by identity to the other components, other connected sum components. And let me define F1 by this copy and extend it by identity to other components. And here maybe I should remark that although I took F as a diffeomorphism in here, but once you extend to other component, it turns just a homeomorphism. At least a priori, there is no guarantee that this extended F turns a diffeomorphism, because this connected sum decomposition is just a purely topological connected sum decomposition. And just similarly, just take another S2 times S2 and take a copy of F here and put a name F2. Okay. And these two guys are obviously commuting homeomorphism, okay, commuting each other. So just by construction. And once you have commuting homeomorphisms, you may get a family over T2 just by pasting the the edge of scalars along F1 and F2. So, and as I said, F1 and F2 are just homeomorphisms. So this bundle is just a homeo bundle obtained as a mapping tools. Okay, homeo bundle. So this is a construction of E appearing in the statement I explained. So the feeling is that since we are using such a connected sum, topological connected sum decomposition, so this family could have some non-smoothability. At least it's not so strange to hope that this guy has some non-smoothability. And what I explained is, yeah, actually it can be shown that this guy is really non-smoothable. Okay, so next I have to of course say how to show the non-smoothability, and so here is some basic principle, not only about the work with Kato and Nakamura. So this thinking are very common for all these kind of recent work. So the basic thinking is to consider a family version of a constraint on smooth form manifolds such as Donaldson diagonalization or Fruita's 10/8. And both of diagonalization and 10/8 are regarded to be constraints on the index, Dirac index, and H plus of X. And these guys appear as a domain and codomain after suspension of a finite dimension approximation of the monopole map. So the basic strategy is to give a constraint on family versions of these two guys. And the family version of Indo D is very obvious, just the family is index living in K theory. And the family version of H plus is not so difficult, and which I will explain later. But here is one short remark. Although it's very natural to try to find the family version with diagonalization or 10/8, but actually there is also a constraint which doesn't have unparameterized analog diagonalization of 10/8. So one example is given with David. So I will explain this H notation, H plus E. This is a family version of H plus. And we may say that the second Stefan Whitney class is 0 for a smooth family of K3 surface. And this is non-vanishing of some characteristic class of this. This is a vector band. And so there's, at least I cannot think of any unparameterized analog of this kind of result. So this suggests that one might be able to get some constant which can't be found in unparameterized normal gauge theory. So it can be interesting direction, I hope. And the proof is done by considering still the square operation on the monopole, family's monopole. And here's the not definition, explanation of H plus E. So the result listed above, detecting non-smoothable families, we are using this invariant H plus E. This is the topological information about family version of H plus E. And so as a correspondence, once you have a family of 4 manifolds, you may get such a vector bundle of fiber dimension B plus and having a common base space B. And this has been already considered by Chanjun Li and Aiko Liu's work about parameterized cyber with invariant. And intuitively, it's very easy to say this is just a bundle of maximal dimensional positive different subspaces of H2 of each fiber. But this guy can be determined by E only after isomorphism, The formal definition is also not so difficult, so let me explain. Just here is, so once you are given a topological fiber bundle, and something important here is not necessarily smooth, just a topological fiber bundle. And let me denote by guru plus R, the maximal positive definite Grassmannian. Namely, the space of maximal dimensional positive definite subspaces of H2 of X. Okay, such a Grassmannian. And this guy is known to be contractible. And this corresponds to the fact that H plus X is unique up to isomorphism. Up to isotopy. Of course, like once you fix a Riemannian metric, then you can get some representative of H plus by considering self-real harmonic two forms. But in general, there is no canonical way to determine it. And since a homeomorphism, of course, preserves the intersection form. So this guy acts on this Grassmannian. And this group action, of course, give you an associated vector bundle, associated fiber bundle with E with fiber, this Grassmannian. So let me denote by this associated Grassmannian bundle. And because, as I said, this fiber is contractible. So this fiber bundle admits a section, and the section is unique up to isotopy. So let me denote by this bundle, H plus E, a section of this Grassmannian bundle. And as I said, this section is unique up to isotopy. So this vector bundle is also unique up to isomorphism, but there's no canonical way to determine. But at least we can use this isomorphism class as an invariant of this fiber boundary. Okay. So the all of recent work I listed detecting non-smooth families are based on the following procedure. Just get a constraint on H plus for smooth bundle E, and next to find a topological bundle E violating the above constraint. And here, technically, something important here is that we have used that H plus E makes sense also for topological family. So otherwise, you cannot state that the topological bundle E violates the constraint. So this is something important. And then you can conclude that this E is not smoothable. And the idea of the construction of such E node, E0, I dropped 0. Yeah, such E0 is just what I described using the pictures. Very simple. So it seems I have not so many times. So let me go to explain the Baraglia's result, describe Baraglia's result.
So what's the constraint you are talking about?
Sorry?
So what's the constraint on the H plus of E you were talking?
Yeah, so let me show you in the next slide here. Okay, thank you. Yeah, I should explain. So to explain that, let me just quickly review the Donaldson diagonalization proved by Cyber. Also cyber. Of course, yeah, all of you probably know this Donaldson diagonalization that originally done by Ian Mills, but one can also have cyber within proof. And the key step is to show that the Dirac index, this is the Dirac index, right? 8 multiplies. The Dirac index is non-positive for arbitrary species structure. And this inequality was extended by David in the following sense. Let X be a closed-oriented smooth form manifold, and let S be a spin-C structure on X. And let me consider smooth family over compact base space P. But here, of course, one should consider smooth family of spin-C structure more precisely, including spin-C structure. And assume that, so here is a constraint I mentioned. So assume that the WB plus of H plus E is non-zero. So WB plus then the Steffi-Whitney class of degree B plus. Okay, so here is a vector bundle which I explained. This is a vector bundle associated to the fiber bundle E. And consider this condition: the WB plus of this guy doesn't vanish. Then we have the same inequality with the Seiberg-Witten proof of the Donaldson's theorem. Okay, the non-positivity of Dirac index. Okay, so as I said, the resulting inequality is just the same with unparameterized case. But of course, the important point here is that originally the assumption was negative definiteness, but it's replaced with this non-zero, non-vanishing condition of Steffi-Whitney class of this vector bundle. So of course, this intuitively this means E is twisted enough from the viewpoint of H plus, and the feeling is that like this: if you suppose that the Wi of H plus doesn't vanish, then it means like B plus is killed by I. So that's a feeling. So if you suppose that the WB plus of H plus E doesn't vanish, then B plus is killed by B plus. And the situation looks like a negative definite situation. So that's a intuition. And so I have definitely no time today to explain the proof, but the proof of this result to extend it for manifold with boundary is the result with Masaki. So that will be explained in the next talk. Okay. Oops, sorry. And yeah, as I showed, so this is the consequence of the David's result. So using this constraint, so this is so precisely I should say this is a constraint on H topological information of the bundle of H plus and the rank of Dirac index. Okay, this is so somewhat important here is that this is just the information of the rank of the Dirac index. So we don't currently no one I think considers the topological information of Dirac index to detect non-smoothable families currently, just since it seems a little difficult. So now we are using topological information of H plus bundle and rank of Dirac index. And using these constraints, David showed this result, which I explained. Oriented closed symmetrical to indefinite for manifold with this signature condition. This inclusion is not a quantum equivalence. And this theorem is a very similar story with the theorem which I explained, the work with Kato and Nakamura. So consider a bundle of some bundle of a torus and consider the obstruction theory. Then you may get some constraint around up to the dimension of the torus. So that's the theorem, the proof of the theorem. Okay, so now I'm already exhausted my time. So as I said, there are two extensions of this various constant with Nakamura and with Masaki, and this extension to form manifold with boundary is the topic of the next talk. So yeah, I hope to see you guys next week. Okay, yeah, thank you so much for today.
So, are there any questions?
Can I ask a question? So can you elaborate a little bit more? What do you mean that B plus is killed by I?
Well, yeah.
Because it's so clearly there is some kind of slang here, which maybe not obvious to some people like me.
Let me see. How can I explain? Like, so maybe I should actually show the proof to explain this more clearly, but more precisely. But let's say, so to prove this kind of theorem using Seiberg-Witten, one way is to consider a finite dimensional approximation of cyber-written map and consider the S1 invariant part of the monopole map. Then you may get such a square diagram. And using this diagram, you can get some divisibility of equivariant Euler classes of some bundle corresponding to the finite dimensional approximation of the spinor bundle. And just looking at that divisibility condition, you may see that actually the equivariant Euler class of this bundle will appear. So equivariant means like circle equivariant Euler class of this guy. But now circle is acting on the form trivially. So actually it is nothing, almost nothing but this guy. And the non-vanishing of this characteristic class finally gives you the same conclusion. But in the negative definite case should be regarded to be W0 of H plus X is non-zero or something like this. So the negative definiteness says just the lowest characteristic class is doesn't vanish. But of course, it's very obvious in unparameterized case. But once you try to extend it to families, the negative definiteness just corresponds to like sorry, very hard to explain without showing proof. Like how can I explain?
Can I ask maybe just in some ways the same sort of the same question that Boris is asking? That I mean is somehow the point, you know, in the with Donaldson's original proof and also even in the Seiberg-Witten proof of Donaldson's theorem for definite manifolds, somehow you see the influence of reducible solutions, and that's where Elke's theorem comes in. So does this assumption about this this characteristic class somehow allow you to bring see the influence of the reducible solutions? Is that somehow the
Yes.
moral?
Yeah, the feeling is precisely like this. So as I said, so in the current proof of this theorem by Baraguri and the extension to homomorphism with boundary with Masaki is done by looking at the monopole map, not the modular space. So it's a little bit harder to get intuition compared with modular space. But as I said, in the proof, we will consider the S1 invariant part of the monopole map. So it's roughly corresponds to considering the reducible part. But if you don't assume this condition, then you cannot extract some information from the downstairs, this S1 invariant part of the monopole map. So this condition is some kind of necessary condition to get some useful information from the S1 invariant part of the monopole map. So in such a sense, this is the condition to get the information from reducible. But I'm not sure if we can interpret it as in terms of modular space, the common space. But the feeling is precisely that we may get some information from reducible by assuming this condition.
So in the theorem, it's so essentially it is an assumption that you have that this bundle has non-trivial Stiefel-Whitney classes. But when you have particular examples when you have such non-trivial bundles of H pluses?
Sorry, I might miss some last words. So when I
do you have kind of so this is so as far as I can see, you have an assumption that Stiefel, so that this bundle of H pluses are non-trivial if using Stiefel-Whitney classes. So how do you construct the examples like this?
Oh, this is precisely this picture. So
this is the first example, right? Okay.
Yeah. Maybe I should explain, but just maybe I missed it. So the reason why I imposes here that every bus is homology orientation is precisely about that point. So for example, in this case, this every bus is homology orientation here and here. So if you take mapping torus for these commuting homeomorphisms, you can immediately see that W2 of H plus bundle associated to this guy doesn't vanish.
I see.
Very, yeah.
Okay. Okay, thank you.
Yeah, thank you.
I don't want to stop questions, but I will remind people that we will be back in 47 hours of the relative grading with Masahiko, or wait, with Masaki, sorry. Also, if you have questions that you think of, you can send them either directly to Hokoto or to me, and I'll forward them and post them, and I'll post the video after it's processed.
Okay, thank you. Thank you.
So Dave's comment notwithstanding, just a quick question about the constraint for K3 families, or the non-vanishing of whatever it was, W2. So is that so there's interesting families of K3 surfaces coming from you know, the classification of K3 surfaces and the Torelli, you know, the in algebraic geometry. So was that theorem known in the you know, in the algebraic case already? Or sorry, you know, if you were talking about holomorphic families, I guess algebraic is something different.
Yeah, currently I don't know about that so much, but at least one thing I can say is that if I remember correctly, yeah, like someone working in algebraic topology, this area says that like if you consider a family of K3, maybe parameterized over two sphere, I think, obtained by just precisely by a global Torrey theorem, would have non-trivial Moita-Manford mirror classes. They can show that, and also it tells you that that family of K3 is non-trivial family as diff bundle, but not only as diffeomorphic family. If I understand correctly, it also implies that that bundle of K3 over two sphere is non-trivial also as a topological bundle. So this is because that the Moita-Manford mirror class is defined also for topological manifold bundle, at least over any field, like over Q, for example. And their calculation is based on yeah, they calculated over Q. So I think the non-vanishing of that Moita-Manford mirror classes of the K3 family over two sphere implies that non-triviality as a homeomorphic bundle. So it's interesting example, definitely, but probably it doesn't extract any difference between diff and homeo because of that reason.
Thank you.
Yeah, thank you.
Well, I think it's worth thanking Hokoto for a lovely talk.
Okay.
I'll look forward to seeing people when we can actually see people in person again.
Bye, everybody.
Bye-bye.
Bye.
Bye-bye.
Bye-bye.